So our next speaker is Kexing Ying, and he's going to tell us about probability and new beginning.
Yes, thank you, Kevin. Well, this summer I've worked on a result in measure theory called the Radon-Nikodym theorem, and this result allows us to do a lot of stuff in probability theory, and I will talk about that. So in particular, as an overview of this talk, I will first talk about measure theory and some basic definitions and a general idea of what Radon-Nikodym is on paper. And then I'll talk about my formalization of Radon-Nikodym in Lean. And lastly, I will talk about what comes next, as in what specifically I will talk about a bit about probability theory and what we can formalize now that we have Radon-Nikodym. So as a general introduction, right? What is measure theory? So in measure theory, we're interested in studying something called a measure, and we have a very good intuition of what a measure is. So in particular, we can think about measures as measuring, for example, length, right, volume, area, or even something more abstract like probability. So intuitively, we measure, or like not more formal, we measure a particular set. So in particular, we would like an empty set to have measure 0. And for disjoint sets S and T, we would like the measure of the union of the sets to be equal to the sum of those measures. With a small caveat, of course, is that we would like it to be also true for countably infinite pairwise disjoint sets. So we have this equality here. So one useful example that we have is the Lebesgue measure, which is defined for the real numbers. And comes up a lot in probability theory in particular, where we have the measure of an interval, whether it's closed, half closed, open, or whatever, is the length is b minus a, right? So we can think about the Lebesgue measure as the length of interval. Yeah, so I denote the Lebesgue measure by lambda throughout this talk. So given a measure mu and a measurable function f, we can construct a new measure, and this is a very important construction. We define a set to have measure the integral of the function on that set with respect to mu. So we don't really need to care about what the definition of the Lebesgue integral is, but we can think about this as it behaves similar to what a Riemann integral is, right? It is easy to show that this is in fact a measure where if we integrate over empty sets, right, we obtain 0, and if we integrate over two disjoint sets, then it's the same as adding those integrals. And this is an important measure because, for example, if we let f to be this particular function, we see that this is a very familiar integral. In particular, this is the Gaussian distribution, right, for the cumulative distribution function for the Gaussian distribution. So yes, so now that we can, with that definition in mind, we can define or talk about what the Radon-Nikodym theorem states. So given two measures, mu and nu, we can say mu is absolutely continuous with respect to nu if for all measurable sets S, nu of S equals 0 implies mu of S equals 0. So in this sense, mu is somehow less than nu, right? In particular, if we have a strict not a strict inequality, but if we have a less equal, if mu is less equal to nu in the function sense, then since the measure is non-negative, right? If nu maps S to 0, then of course mu will map S to 0 as well. So to somehow denote this notion of less equal, we use the following notation where we denote mu less equal to nu if mu is absolutely continuous to nu. Also, a small caveat about the name. Why is it called absolutely continuous? I can talk about this at the end if we have time. So clearly the measure I defined in the previous slides where we have the integral measure, right, is less equal to, is absolutely continuous with respect to mu. So if we're integrating over a null set, it is easy to show that, in fact, yes, if we're integrating over a null set, the integral will be 0. But what we care about is whether the reverse is true, right? So in particular, if mu is absolutely continuous with respect to mu, does there exist a function, measurable function, f, such that mu equals f mu? And Radon-Nikodym theorem states exactly this. In particular, we have actually an essential uniqueness, but I'll talk about that one at the end as well. Right. So now I will talk about my implementation in Lean. Right. So here we have a flow chart of how it was done. In particular, we start off with an object called a sign measure, and then we approve a technical result called Hahn decomposition, of which we are allowed to diverge into two directions. One about results regarding sign measures, and other about Radon-Nikodym theorem for positive measures, so normal measures. Yeah, so I was able to prove and PR everything up to the last point. So we don't have Radon-Nikodym theorem for sign measures yet, but that should be a relatively easy generalization since we have all the previous steps done. So here I have defined what a sign measure is. So a sign measure is similar to a positive measure, where we have it's a set function, right? So it maps a set to a real number. So instead of extended non-negative real number, we map it to a real number, and it maps the empty set to 0. And for all pairwise disjoint sequences, it is countably additive. So this equality holds. And here we have some Lean code, so we can notice a particular difference where we have a definition for a more general object called vector measure. And we define sign measures as an abbreviation, where a sign measure is simply a vector measure of over the reals. So why vector measure, right? So we note that the Radon-Nikodym theorem, or more generally the Radon-Nikodym property, holds for more general measures. In particular, it holds for complex valued measures and also Hilbert space valued measures. And we also notice an implementation detail here, where okay, first and foremost, we have an extra axiom where I state that for a set that is not measurable, it has measure theorem. So normal measures doesn't have this axiom because we have something called a Carathéodory extension theorem, where given a measure, we can pull it back to an outer measure and pull it forward back to a measure. So with that, in Lean in particular, the implementation is we define a measure to be first pulled back to an outer measure and then pulled in again. So throughout this process, every non-measurable sets get somehow normalized, and then we only care about the measurable sets, and the measurable sets are equal if and only if the vector measure, the normal measures are equal. It is not the case for vector measures because we don't have the Carathéodory extension theorem for vector measures. So what we do is we force non-measurable sets to be mapped to 0, and then we can simply compare the measurable sets in order to determine the equality of vector measures. A second implementation thing is that we use has sum instead of t-sum, which is used by normal measures. So the reason for this is for normal measures, we're summing over in reals, right? In particular, every sum is convergent for non-negative positive extended reals. But this is obviously not the case for vector measures. So what we do is we use has sum, and this tells us that if it is convergent, absolutely convergent, then the sum is equal. It is possible to show that every sum of the form where we're summing over the sign measure over this pairwise disjoint sequence is summable, but this is only true from what I've checked, that it's only true for finite dimensional vector spaces. But we know that we're not assuming any of those conditions here. We're just assuming adcom monoid and topological space. So it's not true in general. So with that in mind, we have a technical result about Hahn decompositions. The specific statement is shown here, where it is about, given a signed measure, we can decompose a whole space into two parts, of which one part the signed measure is positive on, and the other part the signed measure is negative on. So this result is a very interesting result, and I will just outline the proof here because I think the proof process in Lean is very interesting. So the general proof follows by creating some sequence of special sets, and these sets converge has measures converging to the maximal in that with respect to that signed measure. So what happens here is we define a mutually inductive sequence where epsilon A1 is defined by epsilon1, and then we have epsilon2 is defined using A1, and so on. So how do we do this in Lean? So what I've initially came up with is a bundled approach where we bundle epsilon n and an together, and we have the next pair depending on the previous. But this is somehow very difficult to work with, and because the sequence doesn't necessarily exist. So the proof actually follows because if the sequence exists, then we have the proof, and if the sequence terminates, then we also have the proof, right? So it depends on the case like that. But it's this difficult to make a definition depend on some existence statement like that. So what I end up doing is a prop approach. So what happens here is we create an existence statement. So there exists some condition, and by using classical.sum, we may choose the pair of in particular the an and the epsilon using that existence statement. So here we have the statement itself, and I have, if you can see here, I have written documentation for it, and so if anyone's interested, they can read on the mathlib documentation website. With that, following the flowchart, we now come to the Jordan decomposition theorem. So this is not the same thing as, obviously not the same thing as the one famous one from linear algebra, but it's also a very interesting theorem in which we classify all signed measures, right? So given two measures mu and nu, where it is easy to see that mu minus nu is a signed measure. So the reverse is also true by Jordan decomposition, and in fact, the decomposition is unique. So given any signed measure, there exists a unique pair mu and nu, such that mu minus nu equals that signed measure. So this is a very important theorem in order to prove not Radon-Nikodym for positive measures, but Radon-Nikodyms for signed measures. In particular, we decompose uniquely assigned measures into two positive measures, and we apply the Radon-Nikodym theorem on those individual parts, and then we can simply obtain the Radon-Nikodym derivative using that way. So here I have the Lean statements for the Lebesgue decomposition and Radon-Nikodym theorem. So the Lebesgue decomposition is here. It's an existence statement, and in Lean, we've decided to make this into a class. So it says there exists some measure and a function such that it's a technical statement, right? So we don't need to go into too much detail, but the main result is we are able to show that a pair of sigma finite measures have Lebesgue decomposition. And with the Lebesgue decomposition is somehow a more general version of Radon-Nikodym, which give us that a pair of measure is absolutely continuous if and only if the Radon-Nikodym derivative. So this is just a lean speak for what I've written in the previous slides, where there exists a function f. So in particular, we have f written as a Radon-Nikodym derivative here. So what's next, right? Now that we have Radon-Nikodym. So probability theory. A large chunk of probability theory, in my opinion, was blocked because we don't have Radon-Nikodym. So one very basic definition in probability theory is the probability density function. It's something we learned in year one, and it's somehow not very easy to do formally in probability theory. And another thing is conditional expectation. It's also something we've learned in year 1, but somehow you use this Radon-Nikodym as well. So what's the deal with probability density function? Well, we know what the cumulative density function is. It is quite simple. It's just simply the probability measure on the set of the pre-image from minus infinity to some x, where x is a variable, right? So we denote. So it is easy to see that this is the pre-image of on some set forms a measure, and we call this the push-forward measure, and we denote that by this little star here, where we have x star p denoting the push-forward measure. So this is how we define a probability cumulative function. And in first-year probability, we define the PDF, so the probability density function, to be the function small f, such that the following equality holds, right? One question is, how do we obtain the probability density function? So that is how Radon-Nikodym comes in. So what is normally done is we assume that if the cumulative distribution function is differentiable, we may simply differentiate it, and the equality follows from the fundamental theorem of calculus. But differentiability is somewhat a really hard condition because, of course, in measure theory, right, we would like to work with functions that are measurable, not continuous, or in this case, differentiable, which is way too strong. So, in fact, we can use Radon-Nikodym. So if we have, so this is a if and only if statement, but I've only written the imply here, but it's if and only if statement. Yeah, so if the push-forward measure is absolutely continuous with respect to the Lebesgue measure, then by Radon-Nikodym, there exists some function f such that the push-forward measure equals some f lambda. So written out without the notations, we have the following equalities, which is exactly what we had in the previous slide for the definition of the PDF. Right. So also another thing is that we don't have or quite have right now is conditional expectation. So what we, in the most general sense, what is conditional expectation? Conditional expectation is so we're working originally with a random variable on a very large sigma algebra, but given new information, we're conditioning onto a smaller sigma algebra. So in some sense, given information, we can restrict the possible events. And then this obtains a new random variable, which we call conditional expectation. But the problem with that is the original random variable may not be measurable on the new smaller sigma algebra. So Radon-Nikodym comes in and obtains this new random variable. In Lean, in particular, we use the measure.trim function, which obtains a new measure given a smaller sigma algebra, and then using Radon-Nikodym, we may obtain the new random variable. So here I have written a small demo of how it can look in Lean. Of course, this is not going to Mathlib ever because it's not very general. In particular, I've used the positive measure definition for Radon-Nikodym. So here we only deal with positive random variables. But we can see the idea here. So in particular, given two sigma algebras, in Lean it is written as measurable space, and we have G is smaller than F, and the measure on F, given a random variable that is measurable and have finite expectation, we can obtain a new random variable from Radon-Nikodym, and this is the conditional expectation. So there are many things to do still. So in particular, we need to generalize Radon-Nikodym for sign measures and Hilbert space value measures. Also, we will need to show essential uniqueness. So this was something that Remy did for Blochner integrals recently, but we still have to need to somehow restrict it back into integrals. Also, we need to develop a basic APIs for Radon-Nikodym derivatives. And this would be easy to do once we have the essential uniqueness. Yes, so that's the end of my talk. So I'm open to questions.